So in this section, we're going to talk about what does the derivative tell you about the original function. So let's say we have the original function here. Here's a function of f. And I want to know what this function tells us about the derivative, and that will help us tell what the derivative tells us about the function. So let's actually start off. Remember, if we're over here, if we look at the tangent line here, this tangent line is positive. So therefore, the derivative would be positive here. Same with here, it's positive. But over here, that tangent line would be negative. Oops, sorry for that. Tangent line would be negative. And so the derivative would be negative. Over here, same thing. This tangent line, its derivative would be negative. Over here, it would be positive again. So the derivative would be positive. At this point here, the derivative is 0. At this point here, the derivative is also 0. And down here, the derivative would also be 0. So that's what it tells us. And it tells us, hey, the function is increasing on this interval here, and the derivative is positive. The function is decreasing here, and the derivative is negative. The function is increasing again, the derivative is positive. The function is constant here, and the derivative is 0. So that tells us that if f prime is positive on an interval, then f is increasing on the interval. If f prime is negative on an interval, then f is decreasing on that interval. And if the derivative happens to be 0 on an interval or just at a point, then f is constant or horizontal on that interval. So with that doing, let's go ahead and see if we can't draw what the derivative, what the function is doing if this is the derivative. So here is my derivative. What I'd like to do is know what the function is doing. So one thing I will point out is that this tells me my function is equal to 1 at 0. So when x is 0, y is 1. So I know I'm going to go through that point there. Now, I'm also going to look at the fact that here, my derivative is 0. Here, my derivative is 0, which means my function has to be horizontal at those points. Most likely because we're negative here, the derivative is negative here. The derivative is below the axis here. The derivative is above the axis here, so that means the derivative is positive here. And the derivative is below the axis here, so that means the derivative is negative here. This tells me that my function is decreasing, because the derivative is negative. We're decreasing down to this point. Then we're going to start increasing again. We need to go through that point. And then we're going to be increasing, and then we're going to suddenly start decreasing again. So it looks like it's going to look something like this. I'm going to go down, it's going to come up through that point, it's going to go up, go down, and then switch around and go down again. So that looks like that's my function. Now, if I hadn't told you that f of 0 was 1, then I could have drawn a bunch of these, just shifting it up or down, because I didn't know exactly what point it went through here. But the basic shape would be the same. It's just a shift of the graph. If the second derivative is positive, then that means that the first derivative must be increasing. Remember, the second derivative is the derivative of the first derivative. So if the first derivative is increasing, then the second derivative must be positive. It goes with the idea that if the first derivative is increasing, if the function is increasing, then the first derivative is positive. Put primes on these, and you get this other statement. So this is how this all works. Same thing is, if your derivative is decreasing, then your second derivative would be negative. So let's see what that means. Let's actually draw a picture of that and see what that looks like. So I'm going to go ahead and draw a picture of a function. We'll look at that function to see what that function is doing. So I might have a function that does something like this, comes down, and goes up again. So looking at this, I can see that my function is increasing. So f is increasing. So f is increasing on this interval, which tells me that my derivative is positive on that interval. Here, my function is decreasing, f decreasing. And that tells me my derivative is negative. Then I'm increasing again. So my function is again back to increasing. And my derivative is now positive again. So now let's just see what's happening. My first derivative is positive, and then my first derivative is negative. So that tells me that my second derivative, if it went from positive to negative, that tells me that my f prime is decreasing because it went from a positive number to a negative number. So it must be decreasing, which tells me therefore that the second derivative must be negative. Here, we went from a negative number to a positive number. So that tells me my f prime is now increasing because we went from negative to positive, which tells me that my f double prime must be positive. Because remember, if the function is increasing, then the derivative is positive. So if the first derivative is increasing, then the second derivative is positive. So now let's look a little bit closer at this curve a little bit. This curve from here to here, to about here, is what we call concave down. So f is concave down here. From here to here, f is now concave up. I want to point out to you that when f is concave down, notice that second derivative is negative. And when f is concave up, notice that second derivative is positive. The easy way to remember this is up things are positive things, so therefore your second derivative would be positive. Down things are sad things, and they're negative things, so the second derivative would be negative. We can write this all down. If f double prime on an if f double prime is positive on an interval, then f is concave up on the interval. And if f double prime is negative on an interval, then f is concave down on that interval. The inflection point is that point when it would change from concave up to concave down. So going back to this picture here, this point right here is where we are concave, where we change the inflection point. We go from concave down to concave up, and that's called the inflection point. All right. Going to an example, a graph of a population of yeast cells in a new laboratory culture as a function of time is shown. Describe how the population increase varies, and when is this rate highest, and at what interval is the population function concave up or concave down. So again, what I want you to look at is that this is the graph of the population of yeast as a function of time. So this is my original function. So this is my f function. Okay. What I want to know is I want to describe how the population increase varies. So one thing I notice is that here we're going to be, if you think about having what the derivative is doing, let's go ahead and draw in the derivative a little bit here. Derivative is the slope of the tangent line. That slope is pretty minor, but this slope is a lot steeper. So we went from fairly not real steep to much steeper, which tells me that my rate of change is increasing from here to here. So from about 2 to about 7, it looks like my rate of change is increasing. So we could say that. From 0 to about 7, the rate of change of the population is increasing. Then, now all of a sudden we look and go, here's the tangent line, and this is steep, but it's not as steep as it was. So if it's not as steep as it was, that means we must be getting less of a derivative. So the derivative is still positive because we're still increasing. So we could actually say the function is increasing over time, but the rate of change is actually slowing down, it's decreasing. So we can say from 7 to 18, the rate of change is decreasing. It's not negative, it's just it's decreasing. So the rate of change of population is decreasing. F is, however, the population is increasing the whole time. But this gives me more to tell me about. So in the entire time, it's increasing, but it tells me more about how it's increasing. It's telling me it's increasing, but the rate of change is decreasing over time. It's increasing at first, and then it's decreasing over time. All right, let's see what the next thing we want to know. When is this rate highest? We kind of answered that, where rate is positive here, but it's more positive here, and then starts being less positive. So therefore, it's at that inflection point where we change. So it looks like about 7. And this is in seconds, I believe. No, hours, whoops. Make sure you always get your units right. Don't want to mess up your units. So hours. So at about 7 hours, it looks like we have the maximum rate of change. And then it wants to know on what interval is the population function concave up or concave down. So we're concave up from 0 to about 7. From 7 to about 18, we're concave down. So C would be concave up from 0 to 7, and then concave down from 7 to 18. You can't go beyond 18 because the graph doesn't go beyond 18. So you have to stop there. We don't know what happens after that. Now it wants to estimate the coordinates of the inflection point. So we know that the X looks like about 7. The Y would be about 300. So it looks like the coordinates of the inflection point looks to be about 300. I'm sorry, 300. 7 is the X value, 300 looks to be the Y value.